Hello and welcome to the second lecture in What is Calculus? So to recap where we left off last time, we talked about the relationship between distance, velocity, and time. And we started with constant velocity, but then we finished up with kind of a conundrum. And that is, if the velocity is not constant, and we want to find the slope of a line tangent at a particular point, the difficulty with that, of course, is that we have only one point. And if we have only one point, how are we going to find the instantaneous velocity, which is related to the tangent line? So I started... The last thing we left off with is finding average velocity, and while that's not the same thing as the instantaneous velocity, it does take us in the direction we want to go. And to see why, what I'm going to do is this. What if we have only one point? So again, we have the secant line. We use that to find the average velocity. And what we really want, we want the slope. These are both slope. What we really want is we want the slope of the tangent line. And that will give us the instantaneous velocity. Okay, this is where we get into the calculus a little bit. How do we solve this issue? So again, I'm going to draw kind of an exaggerated graph here. This is kind of an arbitrary graph that I'm drawing here. I find if I draw the graph accurately to the data points, it will not curve enough so that I need to enhance, in other words, make the curvature a little more obvious. Otherwise, it's going to get harder to see these differences. So let's take time equals 3 here and time equals 4 here. All we know how to find so far is this secant line. Our goal, just to recap, our goal is the slope of this line. So here is what we're going to do. This is where the calculus takes over. We're going to take this point, the second point, which right now is a t equals 4, and we're going to move it a little bit closer and then take the slope again. And then move a little bit closer and take the slope again. And move a little bit closer and take the slope again. So eventually, these 2 points, the 3 and 4, or what is now the 4, what used to be the 4, these 2 points will be so close together that for all intents and purposes, they will be the same point. Put differently, I mean, in other words, I can take the average velocity from 3 to 4, and we calculated that last time. That's 70 miles per hour. Let's take the average velocity between, let's say, 3 hours to, let's say, 3.1 hours. Okay, well, let's go ahead and do that. So that's going to give us d2 minus d1 over t2 minus t1. And, okay, so it's 3.1 minus 3. D1 is still 0. Oh, no, D1, that's after 3 miles an hour, so that's going to be, that's the 90, I believe. Yeah. And over here, we're going to want 10 times 3.1 squared. That's what we're going to want over here. And so we can do that. 3.1 squared times 10 gives us 96.1. And we take that, subtract 90, and divide by 0.1, and we get 61 miles per hour. And so, again, 61 is not the instantaneous velocity either. However, it's closer. You can see if this is 3.1 over here, we're getting closer and closer to the instantaneous velocity, but we're not actually there yet. What we want to do is we want point D2, I should say T2, we want point T2 to approach. This is the big that's the big term with calculus, to approach T1 with T2 with the distance arbitrarily close to 0. What do I mean by arbitrarily? This is basically what I'm saying is this. As I said earlier, we want T2 and T1 to become so close together, ever so close, so that there is an infinitely small distance between them. So that the distance between them, we might find the average velocity from 3 hours to 3 hours and 2 seconds. It's going to be so close that eventually, if we let that become 0, we can overcome the problem we have with not having 2 points. Okay, so enough talk. Let's actually go through how we're going to do this. All right, so I'm going to redraw the graph one more time. And this time, we're not looking for 4, so I'm not going to draw in time 4. I'm going to do this. I'm going to do 3 plus h. Now, what is h? H basically is the change in velocity, the change in time, or more specifically, T2 minus T1. So h is the difference in time. So, and again, let's see. Here's our equation. D equals 10t squared. And so now what I'm going to do is we want to find the slope of the line. Let's draw a little separated here. Slope of the line between T1 equals 3 and T2, that's going to be 3 plus h. Okay. So we got to plug in the formula. We got to plug in the distance formula to see what our y values are, right? Just like we've always been doing. Well, okay, we found this before. This is going to be 10 times 3 squared, and that's going to be 90. Saw that before. Now D2, so what we need here is we need D equals, I should really say D2, 10, 3 plus h squared. So I'm substituting this arbitrary time point for 3 plus h squared. And so I'll just write it this way for now. I'm not. We have to expand it. We have to foil it eventually, but I'll just write it like that for now. Okay, so we're going to do the same thing we did before. We're going to just find the slope between these 2 points. The calculus part of it, is right here. Approach. What happens if we make so eventually what we're looking at, our goal in a sense, let h become arbitrarily close to 0. H is the difference in time, right? If h is 0, see, if h is 0 right now, that's a problem. If h is 0, we're at the point where we only have 1 point. T2 minus T1 would be 0. That would give us 0 in the denominator. We can't have that. But let's start slowly here. Let's plug everything in. And this is going to require some algebra. This is going to require some, foiling and all that type of stuff. But so far, it's just algebra. So we're going to find the velocity, the average velocity, from t equals 3 to t equals 3 plus h. And so we're going to set up like we have d2 minus d1 over t2 minus t1. And so d2 is going to be 10, 3 plus h squared. d1 is 90. t2 minus t1, well, it's going to be 3 plus h minus 3. So that denominator is just going to become h. And therein you see the problem. We can't let h be 0 because then I'm going to have a 0 in the denominator. It seems like a contradiction, but bear with me a few minutes, and I'll show you how we're going to do this. Okay, so we have to expand this out a little bit. So 3 plus h, the whole thing squared. That's going to be 3 times 3, 3 times h, another 3 times h, plus h squared. And then we have 3 plus h minus 3. Well, that's just going to become h. The 3 and the negative 3 cancel. And so we're going to have 10 times, now we have 9 plus 6h plus h squared. And then take this distributive property, so it's going to give us 90 plus 60h plus 10h squared minus 90 over h. And so we can combine these. Again, fortunately, and this is not a coincidence, we see that the 90 and the negative 90 cancel. So what are we left with? We're left with 10h squared plus 60h over h. We pull out an h from the numerator. This is where all that factoring comes in. This is, this is one of the uses for it. And now you see, here's the point. We can't let h be equal 0 because that would give us 0 in the denominator. However, we can cancel these h's out and give us a velocity of 10h plus 60. This is where the magic starts to happen. So just to recap, so what is this? This is going to be the average velocity between 3 and 3 plus h. Okay, we're getting there. Finally, if I let h equal 0, let's think about what that means. If we let h equal 0, this is going to be the average velocity from 3 to 3. Or in other words, the instantaneous velocity at t equals 3. So all you do is plug in 0 for h. So that's going to be 10 times 0 plus 60, and there we have it. Magic. We have just found the slope of a line given only 1 point. Well, that's not entirely true. We did use 2 points. It's just those 2 points are so close to each other. This is what I mean by arbitrarily close. They were so close to each other that for all intents and purposes, they are the same point, and this is going to give us our velocity at 3 hours. That's it right there, 60 miles per hour. Now, we kind of hinted at this earlier. It was in, earlier. Yes, here it is. We found the average velocity, here it is, from between 3 and 3.1 hour. We saw it was 61 miles an hour, so it's getting very close. If we were to take this a step further, I didn't want to make this lecture too long, but if we said 3 to 3.05, 3 to 3.01 to 3.001 hours, if we kept going, we'd see that this 61 would become 60 and a half and 60.1 and 60.00003, for example, and we would see the numbers are getting closer and closer to 60. So there you have it. I mean, there's really not much more to say than that. This is the use of you've just seen calculus at work. The whole point of calculus is getting that h, getting that difference be closer and closer and closer to 0. Now, of course, the next question is, okay, great, we have a formula for 3 to h, 3 to 3 plus h. What if we wanted the average velocity or the instantaneous velocity at 4 or anything like that? Well, we'll get to that a little bit later. But I mean, you know, there is one cost. In other words, one thing, the fact that you haven't had pre-calculus at this point does limit us to some extent, in that, you know, if we had a function or an equation that was not 8t squared but square root of t or t over t plus 1, if we had something a little more complicated, then finding the instantaneous velocity using this method would quickly become very tedious. So if you take a pre-calculus class, you will learn properties of different types of functions, and then in an actual Calculus 1 class, you would go through some more formulaic techniques of finding these instantaneous velocities. So it's not, all your calculations are not going to be this involved, but I feel that relating the ideas of calculus to velocity equations like this and distance equations like this is a good start. I mean, you know, it's not real intense in terms of calculus, but it's a start. I mean, this is what we've been doing, and it basically almost, you know, a lot of first quarter or first semester calculus kind of comes down very much to things like we've been doing here. I want to finish off I want to go back to our previous example, the first example with d equals 40t, where we had that line, the linear velocity, yes. And I want to just kind of demonstrate one thing here. Let's use this line, and I'm going to use the same technique we just used on the linear equation. So I want to find the instantaneous velocity equation. So let's think about how we would do this. So we want to find the average velocity between t1, we're just going to let that be t, and t2, we're going to let that be the t plus h, just like we saw earlier. And so the d1 is going to be the 40t. Again, 40t is our equation. I'm getting it from right here. That's our equation. That's our xy or our td relationship. And d2 is going to be 40 times t plus h. So let's go ahead and find the average velocity. It's going to be 40 times t plus h minus 40t over t plus h minus t, right? So that denominator is going to become h. We're going to get 40t plus 40h minus 40t over t minus t is 0, and we just left with h, 40t minus 40t, and we're left with 40. Well, that's no real surprise. We know the slope is 40 miles per hour, so this kind of demonstrates that this velocity equals the slope of 40. So when I say the velocity of that, you know, the velocity of this equation is 40 miles per hour, and the slope is 40, those are two exactly identical things. Okay, so that concludes lesson number 2, video number 2. In the third video, what we're going to go into, we saw rate, time, and distance, but there are, of course, other applications as well. And so in the third video, we're going to see an application not for rate, time, and distance, but toward money and profit, which is also a very important application to calculus. I'll see you all then. Thanks for watching.